So enter qualitative comparative analysis. So in the political science field, Charles Reagan introduced this method in the 80s. He was studying the outcomes related to democracy across different countries. And he was trying to understand the different conditions inside countries that were associated with different outcomes with their forms of democracy. Okay. Now, he could have looked at one country and tried to understand what was associated with these outcomes, and he could have, or what conditions were associated with certain democratic outcomes, and he could have stopped there. But he looked across many countries, and he had qualitative data, and he said it's difficult to disentangle all the different pathways to democracy that I see across these countries. So he developed a tool for identifying multiple combinations of conditions that are associated with a given outcome. And this tool carries specific advantages over both case-oriented traditional qualitative research, as well as traditional inferential quantitative resource, in that it allows the researcher to analyze more cases. So suddenly you can go from a small n to a medium-sized n. Rather than looking at 3 cases, you can look at 8 cases, you can look at 50 cases, you can sometimes even look at 100 cases, okay? It also carries an advantage in that QCA brings the issue of context to the fore. Right? Now recall, with traditional inferential statistics, we lose a degree of contextualized understandings. This allows us to keep contextual conditions in the model, if you will, even though it's not a model exactly. And it does this by using Boolean algebra. Do we have any mathematics educators in here? Or former math majors? No? Okay. It uses Boolean algebra to surface multiple combinations of conditions rather than rely on the interaction effects that we would usually use if we were looking at a large-scale data set, or rather than relying on single in-depth combinations of conditions that we would see in a single case study. So how do we actually do this? What does this tool look like? Well, the first thing we need to do is we need to pick a case. So you select a case that you're going to compare to other cases. That case can be a teacher, that case can be a student, that case can be an instructional task, that case can be a career outcome, like I'm going to share in an example that I'll use to illustrate this tool in a second. You first need to decide what case you want to compare to other cases. And after that, you need to decide, okay, what conditions do I think shape what's happening in this case? And you choose that based on your own substantive knowledge of the phenomenon that you're studying. Okay, not just theoretical knowledge, but you also base it on what the theory would predict. So one of the advantages about QCA is it allows you to bring certain contextual understandings into your work, and at the same time to also infuse those understandings with what you know about the cases or the phenomenon that you're studying because of what you've experienced through the research process. So it's not completely bounded to predefined theoretical, a predefined theoretical frame. And then you need to define your outcome. What result is it that you're interested in looking at? After that, then you go through 3 steps, which is essentially a calibration step, an analysis step, and then what we call a minimization step in QCA. And the first step is that you want to, when you calibrate, you look at all of your conditions. You say, okay, here are 4 conditions that I think are going to be associated with outcome. Say race, class, the longevity of a principal, for example, and teachers' years of experience. And you can either categorize, you can either create categorical values for these conditions, or you can just dichotomize them. And in the example I'm about to share, this is a dichotomized calibration procedure. And then you create truth tables. And so I asked if we had any math educators or any math majors in here who had used Boolean algebra before or studied Boolean algebra before. And you use truth tables that are essentially spreadsheets that show which conditions are associated with every outcome, and they allow you to essentially count, or they count for you, how many, which condition, or how many times certain combinations of conditions are associated with your outcome of interest. Okay? And we're going to make this concrete in just a moment. Just want to make sure we get the steps out first. And then after you see which combinations of conditions are associated with your outcome, then you have an opportunity to reduce all those sets of conditions to the most parsimonious combinations of conditions by eliminating any redundancy that you see through the Boolean counting, essentially.